Okay, welcome to Recreational Programming in C++, or Recreational C++ Programming. First episode, and yeah, lighting is off. I apologize. It's going to look kind of amateurish, but I wanted to get this out by the 14th because of what the program is about. So let me just get rid of this. And we're going to look at a program. Let's see. Hello. Okay. Obviously, my slides are going to be picture in picture. So, yeah. Let me just get out of the way. And you see pi. Well, now, as you can see over time, there were different ways of computing it. From Archimedes' method, where he basically circumscribed and inscribed a circle with polygons. The polygons, he could calculate their circumference quite easily. And from that, he could work in an upper bounds and a lower bounds for pi. That was a very long time ago. And then you have Madhava's series, which is kind of nice. Don't like having a root, the exponent being what it is. Well, maybe it's not so bad. Wally's product, Euler's formula, Euler's formula, and the big daddy of them all, Ramanujan's formula. Ramanujan was self-educated, unfortunately passed away at the age of 32, which kind of sucks because he probably had a lot of things that he could have brought to light. So what I'm going to be using is derived from Ramanujan. It's called Chudnovsky's algorithm. And I should give it a whole board. But it's a very fast way of converging on pi. In fact, each term gives you about 14 digits, which is pretty cool. And that's just in this form. Now, to do it, first I decided, to break it down into more digestible pieces. So, the first piece is the bit in the beginning of the series. The whole series is multiplied by. And this one function handles it. Now, you noticed I'm using boost. I'm using boost for CPP int and for the MPFR float. And Boost actually is wrapping, the MPFR library for doing large precision floating point arithmetic. And that's a C library, but your eyes would bleed if you saw how to use it. So the Boost wrapper really just makes it so much easier. In fact, kind of makes it trivial. So we have that. And let's bring up another slide. Okay, the factorial. It's used a lot throughout the program. And you would think, at least I had hoped, that using a process called memoization, which works beautifully in a single-threaded application, would work for this program. But, yeah, and it might probably have to do some kind of a thread local storage type trick so that the threads don't share information and therefore require locks. I'm getting ahead of myself with the threads. So I wrote my own factorial program simply because I did not find one in CPP-init or CPP-in. I just didn't, I don't know, I didn't find it, so wrote my own. And let's get rid of that slide. Now the other bit to do is the numerator. And dirt simple little function gives me the numerator. And I like breaking the program down into little bite-sized chunks simply for, I don't know, digestibility. I can fit the little bits in my head, which is going to show up later why the little bits work. So if we go to next slide, I handle the denominator in two parts, even though the two parts are multiplied together. So ultimately we'll have a numerator divided by, denominator A times denominator B, and they have to be converted into floats at this point because of the way C++ handles integer arithmetic. That is, 1/3 in C++ is 0 with a remainder of 1. And a lot of higher level languages hide that from you, but that's what the machine does under the hood. So C++ is still kind of close to the metal. It just gives you a lot of abstractions, or rather the ability to create a lot of abstractions away from the metal to the problem at hand. And that's really one of its great strengths. Also, you're not confined to strictly, object-oriented programming where you have to do these weird design patterns and have object factories and other such nonsense. And you don't do that. There's something called resource acquisition is initialization. And we're going to see a bit more of that in this program. Let's go to the next slide. And this is where the work is done. First, we work out how many threads the machine can run. That is, it's basically a count of CPU cores. So like an i9 on my laptop, I've effectively got 16 cores that I can work with. There's really 8 cores, but the hyper-threading allows each core to do 2 threads simultaneously. It's pretty clever of Intel in that point. The loop, basically, the outer loop is just taking these things called futures, which were introduced in C++11. They're basically nuggets of code that will produce a value at some point in the future, and it's going to run them asynchronously. And the actual function passed in there is a lambda, another feature of C++11. It's capturing a bunch of references that are in scope and a copy of the I value for the loop so that it can distribute the workload over the threads. Because if you're calculating 1,000 terms and you had, for whatever reason, only 10 threads, it would basically have 100 terms per thread all going at once. And the lambda returns a local sum, which will be, as you'll see, joined together. Come on now. In this next step. So what's happening is the futures are having their values added together. And this for range loop blocks on the f.get. F.get will block until that future is finished. So that means you get everything. So your 1,000 terms, or however many you've computed, they all get summed together. And that gets put in, well, because of the algorithm, it calculates the inverse of pi. So at this point, we are taking the constant that we calculated earlier, multiplying it by the inverse of pi, and then, well, actually it's technically the reciprocal, but inverse is the name I've been using. So that gets flipped to make pi. And the very last line on this slide is just, it spits out decimal digits of pi to the precision that I haven't really talked about, but I calculate the precision in the program based on how many terms you want to run the series. Best way to look at the program really is to go to the GitHub, which will be in the description below. And, well, just pull down the code and you can look at it, play with it, optimize it further. There is actually room for further optimization. In fact, my README page has a link to the Wikipedia page, and if you can understand the math for the binary optimization, you can actually make this program faster. So let's have a look at it. Well, one more slide. I'll make this bigger so you can read it, but it shows how The number of digits increases with the number of terms, but so does the time to compute. And roughly, if you double the terms, you multiply by 8 the time. The time complexity is supposed to be O(n log n) cubed. So ultimately, that's just basically saying it's n cubed. I mean, that's the way it works out. You double the terms, you multiply by 8 the time that it'll take. And that's actually a good case scenario because there's memory allocations and deallocations that are going on behind the scene for the large number arithmetic. So let's go and show off a demo run. And through the magic of editing, this is going to be run full screen. So let's bring this thing up. And we have the start of where I did my screen recording of running the program. And I edited it out the computation times because, boring. Now, here I made a mistake. I forgot to give it a number of terms. What are you going to do? So I'll give it 5,000 terms to start. And it churns, and in about 2 minutes, boom, you've got, well, how many digits? Let's find out. I have a shell script, which is also in the GitHub repository, and it's saying we got 70,000 terms compared to a 1 million digit file. It's not bad. And doing a word count now on the file I created. I did a stupid typo. Looked at it a bit. And what's taking me so long here to figure out that I made a typo? There we go. So let's fix that typo. And boom. So we only went 1 byte further than the good digits. And to see what that looks like, there's your 70,000 digits. And that's a lot of digits. It's a lot of pi. Not bad for 2 minutes, and yes, it can be done in less time. Just need a more powerful computer or some optimizations. But yeah, I'm scrolling up and down here just to show off the digits. And also the script output, it shows you where the digit is off. It's only off by 1. That is not bad. So let's go down and try this again with more terms. This time we'll do 6,000, and you'll see what I mean about it taking longer. But fortunately, I've got an editor. So you see it took longer. But this time we got a lot more digits. 84,000 digits. Like I said, that's, 14 times 1,000. So there you go. And we can see that we are off at only the last digit. And we're not generating excessive digits either. So that's pretty cool. And what am I doing here? Oh yeah, had to show off the digits. Like 84,000 digits is going to look different than 70,000 digits. You'll notice the thumb on the scroll bar is smaller. But there we have 84,000 digits of pi. So, and just one more go at showing that it just computed one more byte than needed. And that's the end of that. So let's get rid of that carefully. So what we have there is the Chudnovsky algorithm. It was published in 1988, I mean, by the Chudnovsky brothers. And in case you're interested, the current standing record, it's in Wikipedia, is 100 trillion digits. I don't have the hardware to compute 100 trillion digits. What are you going to do? Actually, the guy who did 100 trillion digits, he bought Google Cloud space to do the job and would have had a supremely optimized algorithm as well. So there you have it. It's a very fast way to compute pi. I'd like to see what Matt Parker is going to be doing for Pi Day this year, because at Stand Up Maths, great channel, and it's kind of become a tradition for him to come up with interesting ways of computing pi, because it turns out there are a lot of ways to compute pi. Some suck. This one is fast. So thanks for watching. Sorry about the studio conditions. Please give me a like if you liked it. Subscribe if you're interested in more. Ring the bell icon too. The usual things that someone shilling their channel will do, because I do mean to come up with more stuff. And I'll see how the scheduling works out. It depends on how quickly I take off, if I take off at all. And some programs might take me longer to do than I expect. That can happen. And I do like to fiddle with things. In fact, the code that I showed you has been fiddled with since recording this video. So that's something to see. You'll see I was trying to do more optimization with regards to the factorial method, so I'm not computing the same numbers over and over again. But I haven't worked out a way that satisfies me yet. Anyway, like I said, likes, subscribes, bell icon, ringing the bell, and there goes my my blackout for a light for a window. So now I've got glare. Oh well, this is as good a time as any to call it an end.